Um, am I audible? Hello.
Yes, ma'am.
Okay. Good evening, all. So just what I was asking, since there was a problem in the audio, that is it okay, like if I switch on my camera, or is it okay, like if I switch off the camera and share the screen with you? Like, are you comfortable, like if I switch off the camera and teach, or is it okay, like if I switch on the camera and teach?
Anything will be okay, ma'am.
For both of you, I guess.
Yes, ma'am.
Okay. So I'm switching off the camera so that you can focus on the screen which I am sharing.
Okay.
Okay, hope the screen is visible.
Yes, ma'am.
Okay, so we are again going to discuss the leftover part of the ISS paper 3 for the year 2020. Here we actually have discussed few questions, two or three questions yesterday's class, and now we are going to discuss the rest of the portions. So we were discussing the portions of sampling. So now moving on to some other portions rather than sampling. So let us consider the portion of heteroskedasticity now. Okay, let's concentrate on this question that describe the problem of heteroskedasticity and how does one detect it. What happens to OLS estimator if we introduce heteroskedasticity? So this question, like we have to divide it into separate. It is already divided, but according to the marks, we need to divide it and we need to write what is heteroskedasticity first, and then we need to see that how this heteroskedasticity actually affects our model and our OLS assumptions. Okay, so first of all we need to know what is basically my heteroskedasticity is, so then we will be in a position to answer that what is the conditions like it is getting violated at the presence of heteroskedasticity. So let us recall a bit the OLS assumptions. Okay, so my OLS assumptions was basically this was my Gauss Markov model having usual notations, and I am taking the order as this is n cross 1, this is n cross p, this is my p cross 1, and as you know, like this will also be my n cross 1, and this is the error vector, and this is the usual Gauss Markov model, and the assumptions corresponding to this is basically expectation of u curl, that is the error is 0 curl, this is one. Number two is the dispersion of u curl is my sigma square into the identity matrix. This has two subparts in it. Now subpart number one is like variance of ui will be sigma square for all I, like when the like we are taking the variance for all the variables to be the same. Number two is the covariance of uy uj is equals to 0 for all I not equals to j. That means this variance covariance matrix or this dispersion matrix will only be a diagonal matrix where the diagonal elements will be, this is going to be a diagonal matrix where the diagonal elements are sigma square only, because the off diagonal elements are 0, which represents the covariance between the errors. That means this is corresponding to this, actually not this one, basically I should write over here, this actually mentions that the errors are not correlated. This is one of the assumption, and the assumption is next assumption, that is my assumption number 3 is basically my rank of the design matrix X, which I consider to be of order n cross p, is less than p, which is a value less than n, is not a full order. And the fourth one is basically this y curl follows a multivariate normal of order n with mean x beta curl and variance covariance matrix like this. These are my assumptions. So what will happen, like if the conditions are violated, that we are going to discuss later. But what is heteroskedasticity? The heteroskedasticity arises over here where we are taking this particular assumption, that is for all I, for all variables we are taking the variance to be same. If my for all variables the variance are not same, then the heteroskedasticity arises in the model. So they say that describe the problem of heteroskedasticity. So this is my usual Gauss Markov problem. Then we are going to write that where we can come across the problem of heteroskedasticity. So we can give some example of situations where we can come across the situations like heteroskedasticity. You can choose any example in the exam to explain this. I am giving you one or two examples for your convenience. Number one is like, let us consider y to be the consumption and x to be the income. And based on this, I am having a model yi equals to beta naught plus beta 1 xi plus uy. Obviously, y is the error. So, usually what we assume that this variance of yi is equals to sigma square. This is the homoskedasticity. Okay, but if variance of yi is equals to sigma I square for all I, that means if this variance varies with respect to this I, then the heteroskedasticity arises, and basically it says that this variance increases with income. We can say this increases with income. This is a situation where heteroskedasticity is arising. Next, going for example number 2, let us consider another example where y is, let us consider the output quality measure. Let it be output quality measure, and let x be income. Okay, so here the variability of y usually decreases with increasing in efficiency. Obviously, since y is the output quality measure, so basically the variability, let me write this, t of y decreases with increase in efficiency. Okay, with increasing of efficiency, that means increasing of variance, and I defined efficiency in the last class as the formula of efficiency is 1 by variance. So variance is related with that. So that means we can actually write variance of y actually is decreasing in x. So if this variance varies with respect to I, instead of variance taking as a constant sigma square, if it varies with respect to x, with respect to I, the variable, then actually heteroskedasticity arises. These are the two examples which where are the situations where heteroskedasticity arises. This first part is taken care by this portion. Next, coming to this first portion, we have already answered. Now, how does one detect it? What happens to OLS estimator when we introduce heteroskedasticity? So, how does one detect it? That is the main question, like when the variance does not takes the constant value and depends on the variable itself and varies with respect to the variable, then the heteroskedasticity arises. So there are many tests for detecting heteroskedasticity. So detection of heteroskedasticity in a dataset will be our next topic. Detection of heteroskedasticity in the data set. So suppose let us consider a array type data. Writing the data in a very short notation for the convenience. This will be my data. So suppose this elements follows normal mu I sigma square independently for I running from 1 to k. Let us write IID. Okay, so this is the data set and I am assuming this as well. So we need to test for a hypothesis. So my testing will be, in this case I am going to consider h naught as whether this sigma 1 is equals to sigma 2 is equals to sigma k, whether they are homoskedastic or not. To test this thing we have basically two three kind of test. Here I am going to discuss three kind of test, so whichever is convenience for you, you can opt that for the exam. Test number 1, Bartless test. In this test, the test statistics is given to be this thing. Let me write this first. Okay, so these are the corresponding elements or corresponding values. So this is the value of my test statistic, which says n star log of SS square minus summation over Ni star log of Si square, where Ni star is Ni minus 1. If you can see, this Ni is basically nothing but the suffix of the data set, like I runs from 1 to k, and Ni is the suffix of j, like j runs from 1 to Ni. So these are the suffix. So Ni is nothing but Ni star is Ni minus 1. So instead of writing Ni, I have just reduced it to Ni star, and N star is summation over Ni star, that is summation over Ni minus 1, which will give you N minus k, because N is summation over Ni, that is the total number of observation which we are having, that is the total number of Yij present in my data set, which I am considering to be a array type data set. So Si square is the particular each and every array type data set corresponding to each column. The standard deviation is considered as Si square, which is 1 by Ni star summation over Yij minus Yi bar square, Yi bar whole square, where Yi bar is the mean of each and every column. And finally, the S square is the final, or I can say the overall standard deviation, which is giving me 1 by, just a minute, sorry, which is giving me 1 by summation of Ni star summation over Ni star Si square, which is nothing but the average of all the sub variances or substandard deviations. Okay, so this is the Bartless test, and corresponding to, based on this, we get the test statistics, and we assume that the under my null hypothesis H naught, where we assume that all the sigmas are true, this T is used to follow a chi-square distribution with n minus 1 degree, sorry, with k minus 1 degrees of freedom, and the data set is going to be heteroskedastic, is said to be heteroskedastic. Let me write this. The data set is said to be heteroskedastic if this capital T is greater than chi square k minus 1 comma alpha, where you know this value you can obtain from the table once you know the value of k minus 1 and corresponding to a particular level of significance. So I am writing at alpha percent, at alpha level of, not alpha percent, sorry, at alpha level of significance. Alpha. Okay, is it clear? Next, moving on to the next test, which is another test, is called Glacier Test. In Glacier's test, we are assuming that, let me write, we are assuming that this sigma I square is increasing in Xij. We have considered like dual type of data where there is a set of Yijs corresponding set of Xijs, and increasing in Xijs, that is sigma I is increasing in square root of Xij. We have just changed it a little bit. So we can write from here one thing, that is not this thing, sigma I is proportional to square root of Xij. So first what we need to do, we need to fit the linear model by oles method. So step 1 will be mine, fit a linear model by OLS method. Okay. Next is if after fitting the model we get an error which is called my EI. So EI, the error is the ith ordinary residual for obviously I running from 1 to n. So EI is the error for the ordinary residual. So we take the absolute value of EI which gives a rough estimate. This EI gives a rough estimate of sigma I. Then based on that we fit a model. Step 2 will be we fit a model which is mod of EI some delta which is the coefficient into square root of xij plus ui for all I running from 1 to n, where delta hat is basically the OLSE, ordinary least square estimate of delta. So in this case basically we need to test that whether this delta is going to be 0 or not. If it is 0 then obviously that is going to fulfill our assumption that whether it is proportionate or not. If it is not 0 then our testing is rejected. So basically the testing procedure over here to give us to test H naught whether delta is equals to 0 against H1 is not H naught. So this is the procedure corresponding to this. My test statistic is capital T equals to delta hat divided by standard error of delta hat, and we can't find out the variance directly, so we need to estimate the variance, and hence we need to get the estimated standard error of this delta hat, which we assumes to follow n-1 distribution under the null hypothesis H naught at level alpha. Okay, so and we conclude that so after testing this thing, so the rejection criteria will be, we may conclude that the data is heteroskedastic. Let me write that. The data is heteroskedastic if, or I should mention this, with respect to xj, if this the observed value of t is greater than this tabulated value of this thing. So this is the case, or these are the two tests which you can apply for basically finding out the heteroskedasticity. So now coming to how you detect it, this portion is done. Next, what happens to the OLS estimators if you introduce this heteroskedasticity? So these is basically one of the major points which we have to discuss. So problems in OLS estimate at the presence of heteroskedasticity. I am giving this heading and writing this up. Problems of OLS estimate in presence of heteroskedasticity. Okay, so what are the problems? Problem number one, that OLS of beta curl is not the minimum variance unbiased estimator. We know when we are using this Gauss Markov setup, we get the estimate of beta curl as beta curl hat OLS, and which is the MVUV of beta curl. But when there is a presence of heteroskedasticity, then beta curl hat OLS is not MVUE. So what we can write? So basically that implies OLSE, just a minute, OLSE estimate, OLSE of beta curl, OLSE of beta curl is not the minimum variance unbiased estimator. Okay. Problem number 2. Problem number 2 said the power of the test regarding beta i's, because whenever we are going to test for the beta i's, that the power of the test regarding beta i's would not be maximum, because we know if we can maximize the power of the test, it is going to give me the how good the test is, and we know that the test should be close to 1. For the power of the test should be close to 1 to get, or how the power gives me that how good my test is basically. So the power of the test regarding beta i's would not be maximum. And number 3 is the confidence interval of beta i's would be wider. We always want the confidence interval to be less wider, or as much as like less the is possible, but it will get wider, like since the, and number 2 and 3 are basically related, since the testing doesn't give you the maximum power. So basically the confidence interval for beta i's would be wider. These are the basic points you need to take care when the heteroskedasticity comes into like the OLS estimate. Other than that, how we can prove that our OLS estimate can affect the above conditions? Okay, so like when we are not like when it is violated, like suppose that we don't use the, suppose like all the variances are not equal, then instead of having this exact OLS estimator, we can't get this OLS estimator, we need to use the generalized inverse formula. That one thing you can add over here. Okay, so we can discuss a particular case for this. So like you can add up a one point, like comparison of beta hat OLS and beta G hat, what we call the generalized inverse. So basically when the OLS assumption is violated, that is all the variances are not equal, in that case we used a generalized inverse, and for that case the we call the model as a heteroskedastic model, and we need to estimate the beta hat according to that. Okay, so since it is not asked over here, I am not discussing that portion corresponding to this answer. Okay, so this one is done. This one we have done in the last class. Let me go through some of the portions of this. I think this we have done already. Penetrating subsample we have done. Okay, we can use this question. Give some practical examples of reasons of lags in distribution lag models, and explain the quack approach of distribution lag models. So we can go on this thing, and as well as, okay, before going on this thing, we need to go with a particular portion of this. Okay, this is actually a practical sum where the quantity for the year 2015 and 2016 for commodities A, B, C, D are given, and for the price for the both the years for the four commodities are given. So they have asked you to calculate last year's price index, Pass's price index, and Fisher's price index for 2016, assuming 2015 as the base year. So this is actually my Q naught, this is my Q1, this is my P naught, and this is my P1. So these values are given. So we need to find out the values of the corresponding index numbers. Okay, so let us try to find this out. Okay, any queries from the previous portions? Anyone, any queries from the previous portions?
No, ma'am.
You're not audible, Shruti.
No, ma'am.
Okay. So let us start the first thing. So can anyone tell me the last year's formula? I'm writing L. Anyone tell me the last year's formula, please? No one remembers the last year's formula. Or passes formula? Okay, let me help you out. Okay, so we actually first read the question, what the price and quantities of the quantity are given, last year's index number. So since the price and quantities are given, so we are assuming that we need to find the price index numbers. Okay, so we are not going into the formula of the quantity index. So last year's formula for price index is summation over I P1I Q naught I divided by summation over I P naught I Q naught I. That means what? The base period price into the base period quantity and their total, the current period price and the base period quantity. So what is over here for my case? For my case, I am not writing any I over here. My case, it is like P1 Q naught and summation over P naught Q naught. So I just need to calculate this thing. I just have to multiply P1 Q naught, that is this column with this column. I need to multiply and I need to add them, and then I need to do the reverse thing like the P naught Q naught, that is this P naught into this Q naught. That means this column is used twice. Okay, then I need to divide it. So I would like to request you to please compute this. Please take a note down this chart and compute one index number last year's and the passes one as well. I'm giving you the passes formula as well. The passes formula says it is summation over I P1I Q1I divided by summation over I P naught I Q1I. So in my case it will be summation over P1 Q1 by summation over P naught Q1. So how to remember this thing? It depends only on the base period in the denominator, and it is basically it gives you the price ratio P1 by P naught, and it takes the weight of the base previous years only. Okay, so how to remember this last year's and passes formula, as I asked you and no one replied me. I don't know whether you remember it or not, but basically the thing is that how to remember this thing, like it takes the ratio of this P1 by P naught. The P1 will be in the numerator, P naught in the denominator, and it always takes care the weight as Q naught. Here also it takes the ratio of P1 by P naught, but the weight it takes as Q1. So this is called last year's price index, and this is passes price index. Okay, so please note down the formula and then you please calculate the last year's and passes index number from this particular table. Okay, shall I stay on this page or in the page of the question paper?
Question paper, ma'am.
Okay, this one. Just any one you calculate. Passes or last year's, any one you just calculate. I think for your convenience, I should write the formula over here as well. This L is equals to summation over. I am writing it in the short notation basically. That is like P1 Q1 that notation. Summation over P1 Q naught by summation over P naught Q naught, and this P is summation over P1 Q1 by summation over P naught Q1. For the Fisher's index, okay, first to calculate it, I should give you 5 minutes time, then I should proceed for the next question. Just asking one thing, I don't want to waste the time. Will you be able to calculate this? I guess yes.
Yes, ma'am.
Okay, so just moving on to the next thing. If they ask you next the Fisher's index, so F is basic. So Fisher's index F is basically, just wait for a minute. So the Fisher's index F is basically nothing but my geometric cross of L and P, that is square root of L into P. But the thing is that you think you should note one thing everywhere where we have like obtained the price index for last year's passes and Fishers as well. So correspondingly we should also know, better to know, just I am giving you the idea that how to remember, and if someone asks you or mention the index number, since it's a very marks and it's very easy to find out, and they didn't mention anything like last year's index number they have mentioned, not price index or quantity index, they have not mentioned anything. So I would say that for the quantity index you can actually use this summation over q1 and summation over q naught. You will give an emphasis on this q1 by q naught ratio, and you will take the weight as p naught for both the cases for last years. Okay, this is L. Okay, and for passes, summation over q1 summation over q naught, you are going to give the emphasis on the weight as p1, that is the current year price. This is price. So these are my quantity index. So one thing we can do, we can write this LQ PQ, and we can write this as P. Okay, so this is my Fisher's price index. So similar manner, I can calculate Fisher's quantity index, which is going to be a cross of LQ into PQ. Okay, so if they ask you for the quantity index, or even if it's possible, or if they ask you for something else, you can use this formula for your easy computation. Is it clear?
Yes, ma'am.
Okay, so please note this down, or I am going for the next question. Let's see what's below we have. Okay, we have another interesting question over here, like define multicollinearity for the general linear model. What are the methods of detecting multicollinearity? Also, the effect of OLS estimates of the regression coefficient and their variances in the presence of multicollinearity between two explanatory variables of the model this. Okay, so we can take here this question now. So we need to first define what is my multicollinearity. So basically multicollinearity, we know that when one of the covariates, or if we have a p covariate model and the covariates are not independent, they are basically dependent, that is known as multicollinearity. So in the context of multiple linear regression, the multicollinearity is the most like important problem, and which is the problem which arises in real life in everywhere. So which are the factors which is responsible for like define, if when we need to define multicollinearity in general linear models, so we need to define the factors which are actually responsible for this multicollinearity. Okay, so before we move on to multicollinearity, I should define that what is my exact multicollinearity. So we are going to define that portion, exact multicollinearity, when we are going to deal with this particular equation. So define multicollinearity for general linear model. For general linear model, the multicollinearity, I am just explaining this portion. Multicollinearity is arises for few of the reasons. Like one of the main reason is like wrongly sampled data on regression, where regressor variables are allowed to vary their values within a very small or short span. So one of my major point is number one, regressor are allowed to vary the values, I should write, within a small span. Number two is like physically constrained model can be used as a multiple linear regression. Physically constrained model means like when we are dealing with like suppose okay, let me write this. Physically constrained model, what do you mean by physically constrained model? Like suppose I wanted to see the income and the house size. These are the basic two variables in a particular model. So obviously it is like they should have a positive relation between them. So obviously the it inherent that if the income is increasing, the house size will increase, or the income has a positive relation with the size of the house. We expect that the people with the higher income are living in a like not a one room or one BHK flat, or in a better size like a bigger house. Okay, this is the thing what we expect. Okay, so but the thing is that and if we add another covariate with it, that is the consumption of electricity with it, so it's obviously going to affect the model positively, because as the house size increases, the electricity consumption is also going to increase. So this is a physically constrained model where inherently my multicollinearity will be there, because all the covariates which we are taking care into, like my house size, my electricity consumption, these two are basically related, and they are having a positive effect on my income, because the income increases, then obviously house size and the electricity consumption is going to increase. So these is called one of the physically constrained model. Number two is misspecification of the model. So like misspecification, let me write this first. Okay, misspecification of the model. It says that suppose you have a particular model where there are variates, covariates are x1, x2, x3, xp covariates are there, but you feel that instead of the covariate x1, there is a high importance of the covariate x1 square, but in by mistake or inherently the covariate x1 is present over there, and or maybe both the covariates are present over there. So since one is the square of the another, so obviously there are going to be a high chance of the presence of multicollinearity in this kind of situation. Next is an overdetermined model. Okay, so like overdetermined model is basically when we have the number of observations is less than the number of covariates. Suppose like we have collected data on, this is a very good example, like we are collecting data on like number of people suffering from a rare disease. So suppose we have obtained data for 20 people, and the covariates like this disease and the effect of these disease and the corresponding covariates which are affecting my model, and the covariate is approximately 25 to 30. So obviously this number of observation n, which is 20, is less than my number of covariates, which is approximately 25 or 30, whatever is the case of consideration. Okay, so in that case it is called a overdetermined model. So in that this is a high chance where we get the chance of detection of multicollinearity or the presence of multicollinearity. Last but not the least, number 5, the time series effect or trend effect. Time series effect or trend effect, we know that time series data are always related, and the data for the last year is related with the data for the current year is related with the last year, data for the last year is related with the second last year, and like this. So sometimes in like time dependent multiple linear regression, it may happen that some regressors what we are considering in the model, like the xt minus 1, xt minus 2, that are related with respect to time. As I told you that the current year data may be related to the past 2 3 years data. So the regressors itself which we are considering in a time series model for fitting up a trend, so that may be related to each other, which may inherently invites the multicollinearity in my model. So these are the situations where multicollinearity takes into place. So these are the cases where we can say that multicollinearity are present in my model. What are the methods of detecting multicollinearity? We all know there are many methods of detecting multicollinearity. Mathematically, VIF, that is the variance inflation function, is the method of detecting multicollinearity. So let me write. Okay, so detection of multicollinearity, one is my VIF, we all know. Number two is like the correlation analysis. So let me write it. Correlation analysis. Number three is VIF, we have already mentioned, auxiliary regression analysis. And number four is so here among these four methods, the most and very important and most popular methods are these two, and sometimes this method are used. This is not that popular. So VIF and eigenvalue analysis, which we can discuss, VI. Okay, let me write the full form of VIF. These are the methods, or these are the what do I say, these are the these are the index which you can use for detection of multicollinearity, whether the multicollinearity is present in your model or not. So you can discuss any, like as per the marks allotted for the question. So my suggestion would be, you can discuss and you can choose and discuss any one method like elaborately, and you can mention the name of all the methods. So let me stop the screen right now, just a minute.